As we will see, the first law of thermodynamics is based on the well-established concept of conservation of energy. However, even more fundamental than this is the basic notion of temperature, and more specifically, systems in thermal equilibrium. The Zeroth Law of Thermodynamics deals exactly with this concept. To help explain the central idea of the Zeroth Law, let's consider two systems labeled A and B. Each is within a container made of adiabatic walls, and each has the same temperature, as indicated by the thermometers. We then replace one of the adiabatic walls in each container with a thin silver sheet and touch them together. The silver acts as a diathermal wall, since it has a high thermal conductivity, which means heat can readily flow through it. Even though heat can flow between systems A and B across the silver sheets, what we find, however, is that no net heat flows between them. No net heat flows because the temperature of the two systems is the same. This shows that temperature is the indicator of thermal equilibrium, in the sense that there is no net flow of heat between two systems in thermal contact that have the same temperature. We will see that if the temperatures of the two systems are different, then heat will flow from the hotter system to the colder one. The thermometers measuring the temperature of each system play an important role. They tell us the two systems are equally as hot. Furthermore, we can consider each system to be in thermal equilibrium with its thermometer, since the temperature of the thermometer must be equal to the temperature of the system. In effect, the thermometer represents a third system. The fact that system A and system B are each in thermal equilibrium with this third system means they are in thermal equilibrium with each other. This represents the central idea of the Zeroth Law of Thermodynamics. Two systems individually in thermal equilibrium with a third system are in thermal equilibrium with each other. The Zeroth Law establishes temperature as the indicator of thermal equilibrium and implies that all parts of a system must be in thermal equilibrium if the system is to have a definable single temperature. In other words, there can be no flow of heat within a system that is in thermal equilibrium. Regardless of where the thermometer is placed within system A, for example, the temperature it measures is always the same.